So welcome again to the tutorials on dynamic system modeling and control. Once again, my name is Hussam Fethi and it's great to have you in this tutorial. The particular goal of this tutorial is to illustrate the process of finding dynamic system equilibria. We defined what a dynamic system equilibrium was in the previous tutorial. Now I want to go through an example or two of how to find dynamic system equilibria. So to be more specific, the goals of the tutorial are twofold. First of all, I want to examine the question of how many equilibria a dynamic system can possibly possess. And number two, I want to illustrate the process of mathematically determine the equilibrium points for a given dynamic system. So moving to the first question, how many equilibria can a dynamic system possibly possess? In order to answer that question, let's go through two different paths. The first path is, let's just count the number of equations and unknowns in the definition of a dynamic system equilibrium. So if you recall the definition of a dynamic system equilibrium, the equilibrium is a point x naught, u naught, and y naught that satisfies the equation that x dot is 0, meaning that 0 is equal to f of x naught and u naught, and y naught is just g of x naught and u naught. So that's our definition, and the question is, how many equations are these and in how many unknowns? So I'm going to declare that the number of state variables is n, the number of input variables is m, and the number of output variables is o, and I'm just going to count equations and unknowns. Now there's a state equation for every state variable. So the vector equation 0 is equal to f of x naught and u naught. I have n of that equation. I have n as many equations, state equations, as state variables. And then the number of output equations is going to equal the number of outputs. And so the equation y naught is equal to g of x naught and u naught. I'm going to have as many scalar equations within this vector of equations as I have outputs. So I'm going to have n plus o equations, and those equations involve the states, the inputs, and the outputs, which means I have m plus n plus o unknowns. And when you look at that, you come to the realization that the definition of a dynamic system equilibrium, as long as we actually have a non-zero number of inputs, as long as the system actually has inputs, the definition of a dynamic system equilibrium that we've explored in both the previous tutorial and this tutorial implies that you're going to have more unknowns than equations. And the question then is, do your equations have a solution? Do your equations have multiple solutions? Do your equations have an infinite number of solutions? How many equilibria can a dynamic system possess? How many solutions can we have to this number of equations and this number of unknowns? It's once you begin to think about that question a little deeper after you've counted the numbers of equations and unknowns that you begin to wonder if for the purpose of making a general statement about the number of equilibria that a dynamic system can possess, whether counting equations and unknowns is even relevant. We're used to this idea in engineering of counting equations and unknowns and making sure that we have as many equations as unknowns to make sure that we have a problem that is solvable. But in some ways, that's just a proxy for asking the broader question of, are the equations that we have solvable? Okay, and I'm not going into the most rigorous details here. I'm sort of making a hand-waving argument to say that the real critical question here is the solvability of the equations representing a dynamic system equilibrium, as opposed to the number of equations and the number of unknowns. That's the critical question, okay? And the second insight is that given the fact that the solvability of the equations is really what's critical, as opposed to the number of equations and unknowns, we come to the realization that a dynamic system can have no equilibria at all, or a single unique equilibrium, or a finite number of equilibria, or as a matter of fact an infinite number of equilibria. All of these are possibilities regardless of the count for equations and unknowns. Okay, so I can construct dynamic systems with no inputs or with many inputs, such that these systems have no equilibria, or a single unique equilibrium, or a finite number of equilibria, or an infinite number of equilibria. Okay, so the next thing I want to illustrate is I want to illustrate these possibilities. I want to illustrate at least a couple of examples to show that a dynamic system can have either zero equilibria or a finite or an infinite number of equilibria. So the next goal of this tutorial is to illustrate the process of determining a given dynamic system's equilibrium point and basically counting these equilibrium points. The system I'm going to explore here is a very, very simple system. It is a mass that is falling under the influence of gravity, and for this example to produce a state space model that has zero equilibria, I'm going to assume that the only thing that is acting on this mass is gravity. There's no aerodynamic drag, and there's no input force. And so in this case, we have a state space model that says that x dot is negative mg over m, or negative g, and y of t is equal to x of t, where x of t is the velocity of the mass, which I'm treating as positive upwards against the direction of gravity. Y of t is also the velocity of the mass, and I'm also treating that as positive upwards. M is the mass, g is the acceleration of gravity. There's no input variable, and there's no friction or drag. To determine the equilibria of this system, all I need to do is to plug in the definition of an equilibrium. And the definition of an equilibrium is x dot has to equal 0. So if x dot is equal to 0 at equilibrium, so x dot naught is 0, that's equal to negative g. And then y naught is equal to x naught. And so I have two equations governing my equilibrium. Okay? Now you notice that the first equation governing the equilibrium says that 0 is equal to negative g. Well, the acceleration of gravity on Earth is 9.81 meters per second squared, and that is not 0. And minus 9.81 is not 0. So these equations are not solvable, and this system, as defined on this slide, can never be in equilibrium. Okay? So this is an example of a system with zero equilibria. Now I'm going to modify the system a little bit and create a new dynamic system that is very similar to this slide, that actually has a single unique equilibrium. So an example of a system with a single unique equilibrium is still the mass falling downwards under the influence of gravity, except there's an aerodynamic drag effect. Now, there's a question, of course, if you're interested in modeling aerodynamic drag very accurately, there's a question as to whether it's linear, quadratic, nonlinear, etc. But I'm going to keep things really simple just for the purpose of this illustrative example. And I'm going to say that this drag effect is a linear drag effect. It's basically as if the mass is attached to a damper with damping coefficient c, and then this damper, the other end of the damper, is then attached to an inertial ground. So I want to build a state space model of this system. The rate of change of the system's state, which is velocity x dot, is 1 over the mass multiplied by the summation of forces, which is minus mx minus mg minus cx. The output y is still equal to x, where again x of t is the velocity of the mass, positive upwards, y of t is the velocity of the mass, positive upwards, m is the mass, g is the acceleration of gravity, c is the damping coefficient. I still do not have an input. So basically I'm summing the forces on this mass, and that doesn't include an input force, and I'm setting that to mass times acceleration. Now if I want to determine equilibria, just like the previous slide, all I need to do is to declare that at an equilibrium the rate of change of the state variables is 0, so x dot is 0, which means that 1 over m multiplied by minus mg minus cx naught, c times the state x, but at equilibrium, has to equal 0. Y naught is equal to x naught. If I solve the first equation for x naught, I get x naught is equal to minus mg over c, and of course what that means is that y naught is also equal to minus mg over c. Minus mg over c basically means that the mass is falling downwards at a constant velocity, but it's not any old constant velocity, it's the constant velocity that makes the gravitational pull on the mass equal and opposite to the drag force acting on the mass. And so when that happens, then essentially what you have is a system that is in equilibrium, moving at a constant velocity. The forces on the system are in balance, and so the only situation that can lead to that is x naught is equal to negative mg over c. So this system has one and only one unique equilibrium. So there are systems out there that can have two and only two unique equilibria and three and only three unique equilibria. I want you to think of a pendulum and think about the fact that the pendulum has two equilibria, one where it's pointing straight down and one where it's pointing straight up. And so we're not going to do that example in this tutorial. If you're taking ME 450 at Penn State, we will be doing this in class. But what I want you to realize is that it is possible for a system to have zero equilibria, one equilibrium, two equilibria, or as a matter of fact, an infinite number of equilibria. So in order to illustrate how a system can have an infinite number of equilibria, let me take the same system again. The system is a mass falling under the impact of gravity, and there's a drag effect, linear drag effect acting on the mass. Except this time I'm going to say that I can apply a force u of t upwards on the mass. Perhaps this mass, is the mass of a rocket, and the rocket is able to apply a thrust force that pushes it upwards, basically. And so in this case, the state space model becomes x dot acceleration is 1 over the mass m multiplied by the summation of forces, where there are three forces acting on the system: the thrust force, the acceleration of gravity, the gravitational force, and the damping force. And y of t is x of t again, where x of t is the velocity, positive upwards. U of t is the input force, positive upwards. Y of t is also the velocity, positive upwards. M is the mass, g is the acceleration of gravity, and c is the damping coefficient. Now, what I would like to do now is to apply the same principle again to determine the equilibrium for this mass yet again. So the definition of an equilibrium is that at equilibrium x dot is 0. So 0 is equal to 1 over m multiplied by the input u, but not any old input, the equilibrium input u naught, minus mg, minus c times x, but not any old x, the equilibrium velocity x naught. And the output at equilibrium y naught has to equal the input, the state at equilibrium x naught. If I take the first equation and the second equation and I reshuffle them a little bit, what I find is that the state x at equilibrium and the output y at equilibrium are both equal to the input u naught at equilibrium minus mg divided by c. And you notice that I can pick any value I want for u naught, and I will get a legitimate value for x naught and y naught and a legitimate equilibrium. So what this implies is that this system has an infinite number of equilibria, okay? Which is very, very interesting. Now, I achieved a situation where the system has an infinite number of equilibria by taking a system that did not have an input and actually adding an input to it. However, I don't want you to be misled by that into thinking that it's the addition of the input that always causes the system to have an infinite number of equilibria. There are certainly examples out there of dynamic systems that have no input and yet they have an infinite number of equilibria. And so imagine, for example, a mass sliding horizontally on a frictionless surface. That mass has an infinite number of equilibria. Whatever its initial velocity is, if you don't apply any forces on it whatsoever, it will continue to travel at that velocity in perpetuity. And so that's an example of a system where there is no input, and yet there's still an infinite number of equilibria. The other thing I want you to notice about this system in particular on this slide is that this system, according to our definition of equilibria in this set of tutorials, has an infinite number of equilibria. Remember, there are many references in the literature where the word equilibrium implies zero input equilibrium. If u naught has to be zero because you're dictating that it is equal to zero, then there's only one equilibrium, and that is x naught is equal to y naught is equal to negative mg over c, and u naught is equal to zero. So whether or not the system has an infinite number of equilibria depends on how general your definition of an equilibrium is. If you adopt the general definition in these tutorials, this system does have an infinite number of equilibria. But if you implicitly assume in your definition of an equilibrium that the input at equilibrium is zero, you're only searching for zero input equilibria. In that case, the system has a single unique equilibrium. So please be aware of the distinction between equilibria in general and zero input equilibria. So what have we done in this tutorial? We've examined the question of how many equilibria a dynamic system can possibly possess. And we've come up with a rather simple answer, which is however many solutions you can find for the equations defining an equilibrium. The second thing is that we've illustrated the process of determining a given dynamic system's equilibrium points. Now, I just want to take a few seconds to explain why this is important moving forward. Very often, we want to control dynamic systems so that they remain within the neighborhood of a desired reference equilibrium. For example, when you operate an airplane in autopilot mode, or when you operate a car in cruise control mode, what you're trying to do is you're trying to maintain a certain velocity, a certain equilibrium velocity for the airplane or the car. So you're trying to operate the vehicle, whichever it is, very near to an equilibrium. So it's important for us to be able to determine what equilibria a system possesses, and then analyze the system for very, very small perturbations around equilibrium, analyze its dynamics for very small perturbations around equilibrium. That will be the topic of the next 2 to 3 tutorials. Until then, thank you very much for watching this tutorial.